Okay, I want to talk to you a little bit about boundary movement work in a simple compressible system. In particular, we want to look at some specific possibilities for work. So, boundary movement work, which we might also call P-dV work. Because, well, because what we're talking about is that work is the integral of P dV. And for many systems, all of the closed systems that we'll look at, we can really consider this as P d little v, where little v is specific volume. So work is the integral of P d volume, but we can also consider that as the mass in the system times the integral of P d specific volume. So as has been stated, in order to evaluate this integral, we need to know how does P vary with V, the volume. How does P vary with V? Or, another way, how does P vary with specific volume? So let's look at some examples. I think this is one that we've seen before. If we have a constant volume system, and this, remember, this is our rigid tank. Because V is a constant, the differential of V is equal to 0. dV is equal to 0. And so if there is no change in volume, there can be no work done. So this brings us to the exciting conclusion that there's no work done when the volume is equal to a constant. Okay, well, next let's consider, and as you wish, we can think about this as on our PV diagram. And this could be pressure specific volume as well as pressure total volume. But this integral represents the area under this curve. So what is the area under this curve? Well, this curve is just a vertical line, and so there is no area under this curve. So the work is 0. Okay, as a second example, we can consider a process where pressure is equal to a constant. And this has been described as a piston that's free to move in a cylinder. In other words, there's no obstruction or any nothing to impede motion of the piston in the cylinder. All right, so if we had a picture of it, then we could make a schematic, something, I don't know. If it expanded from 1 to 2, then the integral from 1 to 2, if P is a constant, and then we just have the integral of dV is just V evaluated at the endpoints, and this of course is just P times delta V. I'm sorry, I think I'm talking a little ahead of what you can see in the video here. Anyway, so if we expand from V1 to V2, then the work done in that process is P goes from dV goes from 1 to 2, and the work is just P times delta V. So notice that the sign of the work is the same as the sign of the volume change. So if the volume increases, this is a positive quantity, and work is done by the system since work is positive. But if we were to start from the larger volume and compress this to the smaller volume, then dV would be a negative number because the second volume would be less than the first volume, and therefore the work would be negative, indicating that work was done on that system to compress that gas. Okay. Yeah, and if we wanted to make a diagram of this on property coordinates, maybe I'm sort of wasting space here a little bit, but we'll squeeze it in right here. If P-V is right here, if we go from 1 to 2, one, 2, that's volume 1, volume 2, then the area under the curve is the integral of P-dV. Okay, so how much worse can it get? Well, let's see. Let's consider a couple more cases. One would be, doesn't come up so often, but if we have a piston arranged in a configuration with a spring mechanism. This is some kind of a spring that has a constant in it, but here pressure is a linear function. I don't know what I want to call this. Let me just call it I guess M for slope. Yes. So the pressure is a linear function of the volume. So the larger the volume is, the stronger the pressure is. This constant M, I mean, you can work this out, but it actually ends up being something like K over A squared, where A is this cross-sectional area of this piston. but I mean, it doesn't matter. We need to know that, but that's not critical for talking about evaluating this integral. So I think if we, hold our mouth right and rearrange this, what is V0? It's this initial volume. P0 is the initial pressure in this inside here. So this is like P0 minus MV0 plus MV. Yeah. So it's some constant A plus MV. And if we were to look at this on a diagram, P versus V, let's see if we can piece that together. It says that at P0 and V0, we have this pressure, and at any other pressure, any other volume, we have a slope M. And so this has that linear relationship between pressure and volume. Okay, so if we want to evaluate the work, and we talked about this with regard to a spring device, compressing a spring, that especially if we look at this from the area under the curve perspective, I think we can see quickly that we can evaluate the area under the curve geometrically from the information on the endpoints without going through this integration, this formal integration. But we'll do it both ways here just for fun. But just from the graph, the area under the curve is what? Work from 1 to 2 is the average height of this trapezoid. So the average height is, according to what I've written there, P0 plus P2. Now, I should have called this V1 and V0, but V1 and P1, but I didn't. So that's the average height, and then I've got to multiply times the width, which is the change there. So we can evaluate that quite nicely from this little formula. But we could also go through the rote mechanics of this integration. If I put in here P0 minus MV0 plus MV dV. So this part is just a constant, and then this is constant times V dV. So I'll spare you a little pain and try to write this out. We're going to end up with P0 minus MV0 times V2 minus V0. That's what I'll get from integrating that first term. When I integrate this second term, I'm going to get M over 2 times V2 squared minus V0 squared. Yeah, and it's not obvious, but this expression is the same as that expression. How can we see that? Well, when V is equal to V0, P is equal to P0. And when V is equal to V2, then P is equal to P2. So in other words, P2 is equal to P0 minus MV0 plus MV2 from here. If we substitute this into here and expand that out, P2 equals P0 minus MV0 plus, and expand this multiplication out, we're going to get some V2 squared and some V0 squared terms, as well as some V2 and some V0. So sparing you the agony of going through that algebra, I'm hoping you can see that if we substitute in for P2 into this expression that we got here, we can arrive at this expression. But regardless, these two things are equal, and we can use either one of these expressions to evaluate the work if we have that linear increase. Okay, the last example that I want to mention is one that will come up in future, and that's going to be PV raised to some exponent n is equal to a constant. In other words, P1V1 exponent n equals P2V2 exponent n. And I just need to tell you that this is not P1V1 raised to the n. In other words, the volume is raised to the exponent, not pressure times volume raised to the exponent. Okay, so I think it's clear mathematically, but sometimes this is misinterpreted and people miscalculate this. So anyway, if we have such a relationship, then how does P vary with V? Well, P is equal to a constant divided by volume to the n. And that, what's that constant? Well, it's either P1V1 or it can be P2V2. It can really be any P in between, but presumably we know P1 and V1 or P2 and V2. But the ability to express this constant in either one of these forms will become useful after we evaluate this integral. So now, I failed to mention, but n can really be any exponent, but it's typically a number between 0.5 and 1.5, or it could be 2, it could be squared, but it's usually in the range of, 1/2 to 2 or 3. But anyway, this will come up more later. Let's look at this integral of P-dV. That's the integral of P, this thing over here, and I can rewrite constant. Well, the constant I can take out. I'll rewrite that right now. Constant v to the minus n dv. All right. There's just my constant. Can't quite see it very clearly. If I come back to this next line then, if I integrate v to the minus n dv, that's like x to the n dx. That's 1 over n plus 1, x to the n plus 1, right? I don't know if you can quite see that off the edge of the page. So this integral becomes my constant, whatever that is, times v to the 1 minus n divided by 1 minus n. And then I got to evaluate that between 1 and 2. And this becomes the reason why it's good to be able to express this constant either in terms of P1V1 or P2V2, because when I evaluate this at the end points, this expression right here, I'll have V2 to the 1 minus n, and where I have V2 to the 1 minus n, I want to use as the constant this expression. And where I have V1 to the 1 minus n, V1 to the 1 minus n, I want to use this expression. And that will allow me to combine these terms with the volume and simplify this expression a little bit. So if you'll allow me to maybe jumble some of that together. P2V2 to the n times V2 to the 1 minus n minus P1V1 to the n times V1 to the 1 minus n divided by 1 minus n. Okay, so again, that's this constant times v to the 1 minus n, constant times v to the 1 minus n, minus the constant times v1 to the 1 minus n. So where I have like exponents, these can be combined by merely adding these exponents together. So when I add v to the n to v to the 1 minus n, I just get v. In other words, that n and that minus n annihilate each other, and I end up with P2V2 minus P1V1 divided by 1 minus n. Okay? All right, well, I think that that is a summary then of the boundary movement work for 3 types of processes that you might see. The first one is very trivial, and that is the constant volume process. But it's important to realize that when there's no volume change, there can be no work done. The second example is for a constant pressure process, and when the pressure is constant, then the evaluation of this integral is trivial, and we can evaluate it either graphically or from the calculus, and we just find that the work is equal to the pressure times the change in volume. The third example was for the linear spring, where the pressure increases linearly with the volume. And in this case, the graphical evaluation is the more straightforward, that we just need the average pressure during that process multiplied times the change in volume for that process. Or we can go through the calculus and come up with a slightly more glorious expression, but will give us the same numerical result. And then the last example that we saw, I didn't tell you the name of this process. I should have done that. I'll do that now. This type of process where pressure times volume raised to an exponent is a constant is called a polytropic process. And for a polytropic process, where PV to the N is equal to a constant, then we can go through the calculus and find that the work done during that polytropic process can be calculated from P2V2 minus P1V1 divided by 1 minus N. There is an exception to this rule, and maybe I'll talk about this another time, but if N is equal to 1, obviously this expression can't be used. When N is equal to 1, this result is not useful. So when N equals 1, we need to reconsider this integration when N is only equal to 1. And when N is equal to 1, then we get a slightly different expression here. I think some of you can figure that out. Integral of dV over V when N equals to 1. Yeah, it turns out to be the logarithm function rather than this polynomial expression. But regardless, when N is not equal to 1, P2V2 minus P1V1 over 1 minus N.